Cisco instructor Andrea here, and before we get started with the module for review, I just wanted to give you a few little reminders about time management. First of all, just keep plugging away. Do the reading, review videos, find what works best for you for getting this information. Is it watching this video? Is it reading the entire module? Is it looking at supplemental videos? Is it listening to the audio recordings? So figure out what works for you. Remember, the first couple weeks are the toughest. You are figuring out how to navigate the class, how to navigate Net Academy, how to navigate Canvas, what is the different assignments. So don't be too hard on yourself. It smooths out after around week 3, 4, definitely halfway through, we'll be on a good steady path. Also remember, we're not trying to become network geniuses in the first 4 weeks or even this first class, right? That's something that's going to come with time and experience. We're just working on getting your feet wet. Also, just get with a tutor or even with me. We have a lot of support and help. And what I've discovered is students that reach out for help, they're often the most successful at doing well in this class. Module 4 is about media. Now, media in networking terms is the equipment or the components that allows us to connect devices together. These modules are set up pretty much to follow the OSI model, which is what we covered in Module 3. So remember, the OSI model is the protocol suite that describes the way data moves through a network. Media takes place at layer 1, the physical layer. So we're talking about the physical components that allow the data to move through a network. I just want to do a quick review on the OSI model. Could you name the 7 layers of the OSI model? Either top to bottom or bottom to top. A good way to remember that and remind yourself is all people seem to need data processing. Now there's a bunch of these, so if there's one that works better for you, find it. I can say that forward or backwards. So application, presentation, session, transport, network, data link, physical. Or I could do physical, data link, network, transport, session, presentation, application. Whichever works for you. Now we're talking about the physical layer, which is that layer 1. The physical layer is where the bits are being transported across the media. In Module 3, we talked about the encoding process, where the transmission is being encoded into something that will move across the media. The networks work in binary, 1s and 0s. But once it hits the media, which is either going to be a fiber optic cable or an Ethernet cable or maybe radio frequency, it has to be transmitted or translated into a way that the media can understand. So Ethernet would understand electric impulses on and off. Light is going to understand light waves, right? On or off. Radio frequency, that's going to understand radio frequency waves where we have a peak or we have a plummet, a peak or a plummet. So the physical layer is going to accept a completed frame from layer 2, which is the data link layer. It encodes the bits into a series of signals that get moved across the media. This is the last step in the encapsulation process. The next device in the path to the destination receives the bits and re-encapsulates the frame. Then it decides what to do with it. Some of that sounds a little complicated, but it will start to make more sense as we move through these layers. Sometimes in this class, you're going to hear terminology and we're going to learn about some information that doesn't quite make sense until we keep moving through the layers. For example, we haven't talked a lot about the data link layer yet. So when we hear this accepts a complete frame from the data link layer, well, if you don't know what the data link layer does yet, that might not make complete sense, but the next modules deal with the data link layer. So we just are starting with the physical layer. What is the PDU at the physical layer? This is again something we talked about in Module 3. I'll give you a little hint. The mnemonic again is don't send pets for beer. Did you get bits. This beer represents the bits. Each layer of the OSI model or the TCP IP model, whichever one we're looking at, as the data is moving from layer to layer, that piece of data is just called something else. So once it hits the first layer, it's actually called the bit PDU, the bit protocol data unit. There's a lot of characteristics and components to the physical layer. We're going to cover a lot of it in this video review. I want to remind you that this is just a video review and we do touch on a lot of stuff. Certainly I try to highlight the most important things, but it is by no means an exhaustive example of what Module 4 will cover. We're covering the highlights. So first of all, each of these different layers have different standards that dictate how they behave and or what has to be implemented at those layers. So the physical layer, we're going to have physical components, the actual physical things. Another thing that happens at the physical layer is that encoding process, where we're changing from bits, ones and zeros, to a transmission that's readable by the media, and then something else called signaling. Now we've talked about encoding and we'll talk more about it here as well as we'll talk about signaling. The physical components are actual hardware devices, the actual media, so the cable, it'll be things like NIC cards, the RJ45s, biscuits, anything that's related to layer 1 that allows us to connect to the network. A physical connection to a local network must be established before any network can communicate. Even when there's wireless, we still have to have some sort of physical connection initially. The physical components are going to include things like a NIC card, the network interface card. That is the interface where you plug the cable in to your laptop or plug the cable into your desktop. There's different types of connections. Okay, here we've got an embedded wireless antenna. So an antenna would be part of layer 1. Ethernet ports, the actual physical ports on a router or a switch that we can see. Here we've got an example of an extender. So this might be something that you have in your home or in your small business that helps push your Wi-Fi signal out to locations that maybe it wouldn't normally be able to get to. These are the different organizations that are going to manage the standards that are taking place at the physical layer: ISO, EIA-TIA, ITUT, the ANSI, and IEEE. It's a good idea for you to start making some flashcards or maybe a spreadsheet with some of these different organizations and standards. It's kind of my least favorite part of studying for the CCNA because I haven't necessarily even myself committed all these to memory. I mean, I'm pretty good with IEEE and the wireless standards, but whenever I take an exam, I have to just restudy them and kind of relock them into my brain. Review question. What is the process of converting information into another acceptable form for transmission? Let's go so far as to say that we're converting the bits. So we're converting information into an acceptable form that can be transmitted across the media. We talked about this in Module 3, and we've actually already talked about it in this video. So did you get encoding and decoding, right? That is the process of using our ones and zeros to convert it into a signal that the media can understand. Remember this from Module 3? So encoding, this is the method of converting the stream of data bits into a predefined code. The physical layer standards must define what type of signal represents a 1, the on, and what type of signal will represent the 0 or the off. The method of representing the bits is called the signaling method. It's how we're signaling the way the data is going to be transmitted. Signaling. The signaling method is how the bit values of 1 and 0 are represented on the actual media. The method of signaling varies depending upon what the media is. Electrical signals are going to be on and off, and voltage is what does that signaling. For light, it's pulses of light. My pulse of light is on, or my pulse of light is off. And then radio frequency signals, right? That is how we are going to signal for Wi-Fi. And notice here that we have a digital signal. Here's our AM and FM and PM. So these are ways in which the radio frequency can be signaled. What are the three forms of network media? If you've read the module already, you would know this. Now, you might also know it because of the conversations that we've been having, or you may have experience with this in your home or your job. Copper cable, that's the first one. It signals using electrical pulses. Fiber optic cable signals using light. Wireless signals using microwave transmission. Again, just a little picture here, similar to the previous slide, showing the way that these signals are going to come across if we were to be able to physically look at them. Bandwidth is another important characteristic and something we talk about all the time. Do I have enough bandwidth? Is there enough bandwidth to watch this movie? Is there enough bandwidth to download this music, download this movie, etc.? What is bandwidth? It is the capacity of the media. So in other words, it's the capacity of the Ethernet cable, it's the capacity of the fiber optic cable or the radio frequency transmission to carry data. What is its capacity to carry data? How much data can it carry? The bigger the bandwidth, the more data that can go through it. So digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time. So imagine the bigger the bandwidth, the more data can flow through. If you think about it like a highway, if you have a 4-lane highway, you can have 4 cars traveling side by side at the same time. If you expand that to an 8-lane highway, you've just gone from 4 cars that could travel in that highway at the same time up to 8 that can move through. In the learning resources, we've linked another outstanding video about all of the physical media characteristics. I would strongly recommend you watch that video. It's only like 7 minutes, and it explains everything that I'm covering really, really well. Okay. Bandwidth is sometimes thought of as the speed that bits travel. That's not really the case. In both 10 megabits and 100 megabits Ethernet, the bits are sent at the speed of electricity. So they're sent at the same speed. The difference is the number that can be transmitted at once. So remember, maybe 10 megabits looks like this, right? Whereas 100 megabits look like this. 1,000 looks like this. So in that same space, I can send more bits per second. A unit of bandwidth is measured in bits per second. 1 bit per second, that is the fundamental unit of bandwidth. So we pretty much will always be talking about bits per second, kilobits per second, megabits per second. A kilobit, right? That's going to be 1,000 bits per second. So again, let's say right here, I could line up 1,000 bits and move it through. Now, as I move up to a megabit, right, I've just gotten bigger. Now I can send 1 million bits all at the same time. A gigabit, 1 billion, right? And then a terabyte, I don't know if that might be a trillion, but a lot, right? A lot. Other important physical layer terms that relate to the bandwidth terminology is going to be latency, goodput, and throughput. What I want you to do is take a look over here at these different definitions, and I want you to see if you can match up where these terms belong. Let's start with latency. Is latency the measure of the transfer of bits across the media over a given period of time? Is it the amount of time for data to travel from one point to another? Or is it the measure of usable data transferred over a given period of time minus traffic overhead for establishing sessions, acknowledgements, and encapsulation? Think about this, the amount of time. This is a measurement of time only. So if you think of it in terms of time, which one of these sound like it might relate to time. Did you pick latency? If you're late, that's a measurement of time. So use these little words to help you put the pieces together when you don't know the answer. Good put. Let's think about this one. The measure of usable data. Okay, so that's the good data. Notice what this says, minus the traffic overhead. There's stuff that we don't know about yet because we haven't learned it. But when we establish like this WebEx session, for example, or this recording session, what has to happen is it takes some bits to establish the actual session before we can start this recording or start viewing a video. Well, we want to take that out of the picture when we're determining exactly what ends up at the destination. That's why we minus traffic overhead. And that's why at the other end, whatever is the final output, that's the good put. Lastly, throughput, the measure of the transfer of bits across the media. So that's kind of like everything that's going across. This little I here is just to let you know that we have some additional information available to you in the learning resources. Okay, it looks like this might be a good time to take a break. We're going to move into talking about cabling next. Can you name the 3 different types of copper cable? This is probably running through your house, or if you, maybe your place of business or businesses that you frequent. The first one and the most common is called UTP cable, unshielded twisted pair. We have some of this in the lab and we'll be using it for some different types of connections. If there's time, we'll even do an extra credit lab where you can build a UTP cable. Next is a shielded twisted pair. This is similar to a UTP cable, however, it has an extra layer of protection called a shield in order to protect it from EMI and RFI. Now, this is more expensive and it is difficult to install because it's so much more stiff, but it does give you a better quality signal. Lastly, a type of copper is a coaxial cable. Here in Arizona, if you subscribe to Cox Cable, you may be familiar with coaxial cable. It uses 2 conductors that share the same axis point. It was used extensively in early Ethernet installations, and again, we still use it in cable. Here's an example of an unshielded twisted pair. It just has a regular, like, rubbery plastic coating around it. Here's our shielded twisted pair. So if you can see here, there's kind of like a little layer of aluminum around it. Plus it has this center post, which is a very stiff plastic little tubing to add strength to the cable. And lastly, here's an example of coaxial cable. There is our center copper right through the middle. It's got a little bit of buffering, and then we've got the copper wiring on the outside. This is to help protect it from EMI and RFI. And just like these others, it still has a rubbery plastic coating on the outside of it. Let's think about some characteristics of copper media. First of all, it's very easy to install relative to other types of media. Data is transmitted on copper cables as electrical pulses, right? The on and the off. The signal deteriorates what? The longer the signal has to travel. So in other words, I could not run a copper cable from Central Phoenix to Mesa, just one long cable, and think that you're going to have any type of a good signal at the other end. And the reason is because of signal attenuation. If you think of this just kind of like degradation, when I first send the signal, it's a good, strong signal. But as it starts to run down that cable, it gets a little worse and worse and worse until ultimately there's really nothing left because the signal can't be pushed at great long distance. The timing and voltage values of the electrical pulses are also susceptible to interference. Okay, so again, turning something off and on, and sending that voltage across the media, there are some interferences that can invade that media, if you will. So do you know what those are? Electromagnetic interference is one, and the other would be radio frequency interference. So EMI and RFI. This is kind of a downside of copper. They are susceptible to EMI and RFI. Now, we've done things to the cable to help prevent that and mitigate it, but it doesn't eliminate it completely. EMI and RFI can distort and corrupt the data signals being carried across the media. Crosstalk is a disturbance caused by the electric or the magnetic fields of a signal on one wire to the signal in an adjacent wire. Okay, so in other words, it's kind of like bleed over that's interfering with each other. Here's an example of pure digital signal. A 1 is an on and an off. A 1, and off and off. So you can see here we have this nice clean signal. Now, what would it look like with interference? And this could either be EMI or RFI. Take a look how it is just jumbling up this whole thing. So how could you tell, is this an off or an on? That signal isn't going to make it to the destination. Now, here's an example that's a little bit different, right? It's actually messing up more of the ons than the offs. Same thing. It is not going to make it to the other side. Okay, so this is just an example of the way the EMI or the IFI interference can be affecting your Ethernet cable. One of the things that we can do to mitigate this and to cancel out essentially the effects, the negative effects, is UTP cable will use pairs to create opposing magnetic fields. Because remember, a magnetic field can affect it. So what we've done is we take these two different colored cables or copper wire and we twist them, right? We use a pair. That way the magnetic field more or less cancels itself out. Okay. To further enhance the cancellation, the effect of the paired circuit wires, the twists are changed. Okay, so I want you to look here. If you look at this brown cable, right here is where they cross, right here is where they cross, and then right here is where they cross. And let's compare it to the blue cable first of all. If you look, these crosses are much closer than the brown. So the brown, the green, the blue, and the orange, they're all going to twist at a different length, okay? They're going to twist at a different length. Also, we can wrap this in a metallic shield. That was the shielded twisted pair. I don't have a picture of that, right? Oh, I think I do. There we go. That is going to be with the shielded twisted pair. So it's just one of these, but it's got this like a tin foil wrapped around it, as well as it has the center post. There are different types of connectors that are used for UTP and STP, but here's an example. Your Ethernet cable is going to have an RJ45 connector at the end. Now they're going to need to be able to be plugged into an RJ45 socket. Now we can see right here, maybe you can make that out. This is actually a Cat5. Here's our punch down block so that we can punch down the different color schemes. And then we have an example here of the RJ45 connectors that have been terminated. And sometimes you may have to build a cable as a network administrator or someone that's connecting up devices. If you don't have any, maybe you need one that's a specific length. This is a poor job because it's left these wires exposed. A much better job would be to get that RJ45 all the way down so that it's clamping onto the actual plastic sheet. UTP Cabling Standards, we've got Cat3. It's never used. I don't think there's any application for a Cat3 anymore. You can see here there's no twists at all on a Cat3. And then we've got a regular Cat5, Cat5e for Ethernet. And here we've got the twists in order to mitigate the EMI and the RFI. Also, it lets us know what speeds. So Cat5 can support up to 1,000 megabits per second. That is another advantage of using Cat5. And then we have Cat6. Cat6 is really a lot like Cat5 as far as its speed capabilities. It's going to be 1,000 megabits per second. Although it does say that you can carry up to 10 gigs per second, it is not recommended. The primary difference with Cat 6 is that it has an additional separator between each of the colored pairs, which allows for higher speeds. What we're seeing right now is definitely if you are working in industry and you're doing a commercial building, they're going to be using Cat 6. I've noticed more and more home builders are also using Cat 6 and or putting fiber optic in a home in order to support something called FTTH, fiber to the home. UTP Cabling Transmission Standards. Look, let's not even think about this Cat 3, okay? But Cat 5e, this is the most common standard. 1,000 megabits per second. The maximum bandwidth is 100 megahertz per second. You're almost never going to see anything less than this. Even now, you won't see regular Cat 5. You're always going to see Cat 5e. Cat 6 is definitely growing in popularity. Notice the reason. We can get this in UTP or STP. It's right here. This maximum bandwidth, 250 megahertz. That's why we're seeing this definitely installed in more and more homes. And then Cat 6A, I don't know. I'm not seeing that installed in homes very much, but certainly it's going to be in some business applications. Lastly, a Cat 7. SSTP. Again, it's only going to be in shielded twisted pair. But here's the beauty, right? As you go up in category, you're increasing your bandwidth. What are the three types of UTP cable? And what are the end standards? In other words, how are they wired up? Okay, let's take a look. So what I want you to think about right here, and what I want you to remember is these standards, T568A and T568B. Let's start with those two. What makes an A and a B different is the way that the wires are terminated into the RJ45, okay? A T568A is going to start with the green pairs, white, green, solid green. Then they're going to have a white orange, which goes to a solid blue, to a white blue, back to a solid orange, and then a striped brown and a solid brown. There's always going to be a striped color first, so it's going to be striped, solid, striped, solid, striped, solid, okay? A's start with green. Now the B's are going to start with orange. And instead of separating the oranges, the greens get separated. When you're doing your labs and you're on campus, I want you to take a look at a cable and I want you to look at the ends or look through the RJ45 and see these color patterns. Now, depending upon what you have on each end, will determine whether or not you have a straight through cable or whether or not you have a crossover cable. Now, a straight through cable is when you have the same termination at both ends. So on this end, I'd have a green, green, and on the other end, I'd have a green, green. That would be a straight through. Now, that means I have a 568A on both ends. I could also have a straight through with a 568B. Okay, so that means I've got a starting pattern with orange, and on the other end, the terminating end, I have a starting pattern of orange. So all a straight through means is that my starting and my terminating pattern are exactly the same. Either a 568A or a T568AB. Doesn't matter, but it runs straight through. A crossover cable is when on one end, my starting end, I start with a green. And on my terminating end, I start with an orange. So in other words, I have a 568A on one end and a 568B on the other end. They're crossed over, okay? That's a crossover cable. And then lastly, we have something called a rollover cable. Now, a rollover cable is usually a ribbon cable, and I'll show you an example of this on the next slide. And we usually cover this, and we'll show you an example in class of both of these. Okay. When do you use each one? I would use a straight through cable if I am connecting two devices that are different. In other words, if I am connecting a computer to a switch, I have to use a straight through cable. If I'm connecting a switch to a router, I have to use a straight through cable. When do I use a crossover cable? I use a crossover cable when I'm connecting two devices that are the same. So if I'm connecting a switch to a switch, I would use a crossover cable. If I connect a router to a router, I would use a crossover cable. Now here's a tricky one. I have a computer and I'm going to connect it to a router. Do I use a straight through or a crossover? Now initially you think, well, a computer and a router, those are totally different. So I'm going to use a straight through cable. Actually, that's not correct. We want to think in terms of these devices' brains. The brain of a computer and the brain of a router are very similar, or the language that they speak at their NIC cards is very similar. It's the same. So because their brains and the language, the way that they speak to each other is the same, we're going to use a crossover cable when you need to connect a PC to a router. Lastly, this rollover cable. Well, a rollover cable is basically a console cable. Remember, a console cable is a cable that we plug into a router or a switch so that we can get into it to manage it from our console PC. So I might have a PC and I plug a console cable into it. Then I connect that console cable up to a router. Now I can get into that router and I can add configurations and I can add commands. It's what allows me to get into a device out of band, outside of the network. Now, a rollover cable is called a rollover cable because if you look here, the colored patterns are exactly rolled over. Okay, they're exactly the opposite. 5, 6, 8 A and B's were splitting the orange pair or we're splitting the green pair. But with rollovers, we're literally just flopping them. There's a lot of different ways to test your UTP cables. Using a wire map tool is probably the best and the easiest way. If we have time in class, we may test that and play with some of these. They're very user-friendly and they're easy to do. I'm going to tell you something I think I've said in another video, and that is the two most common mistakes that are made in networking, especially for beginners, is IP addressing and cabling. Always check your IP addressing and your cabling. Did you plug your cable into the right port? Are you using the right kind of cable? Is the cable damaged? Etc. Let's just take another break before we move into the next section, which I believe is fiber optic cable. The next section is about fiber optic cabling. This should be an easy question for us to answer because we've already talked about it a little bit. Fiber optic uses light pulses, right? Fiber optic. Fiber optic cables use lights to represent the bits. So when the light is on, that's a 1. When the light is off, that is a 0. Fiber optic cabling have a lot of properties that make it very desirable. There are some problems with it. First of all, it's very expensive, but it's perfect for some networking scenarios. It can transmit data over a really long distance at a higher bandwidth. If you remember, we talked about RFI and EMI with our copper cables. There's none of that with fiber optic cable. It's not affected by radio frequency. It's not affected by electromagnetic. There's no interference. It is very flexible, but within reason. Like you can't do like a 90-degree bend on it or fold it over. It is more, it's gotten better and better, so it can do a lot more, but it is a thin strand of glass that can break. You can use a laser or an LED light to encode the bits. Laser will always be used for something called single mode fiber. An LED could be used for the multi-mode fiber. The fiber optic cable acts as a wave guide to transmit the light. So in other words, the cable is just kind of, as the light gets in there, the cable is just kind of keeping the light from bouncing all over the place. Fiber optic cable. It is made up of two different kinds of glass. Okay, first of all, the core, that's the center most pure part. Then the cladding, the glass that surrounds the core. Okay, so if you look right here, and it acts as a mirror to keep the light inside the core. There's two different types of fiber. We've got the single mode fiber and the multi-mode fiber. Notice the difference here. The core of the single mode is 9 microns, whereas the core of a multi-mode is 50 microns, so it's significantly bigger. The cladding is the same, okay? And the coating might be a little bit different. It will always be a polymeric coating on single mode. Multi-mode, it's usually polymeric, but it may have a different kind of casing. This is a very small core, and it uses lasers, and it will only work with lasers. And the reason is because single mode fiber is used for really long distance transmission of data. The multi-mode is less expensive. It uses LEDs to transmit light at different angles, and it can go up to 10 gigs over 550 meters. So still a really far away, better than like DSL, but not as far as single mode. So it can be used in different types of industry. Enterprise networks, which is what we're mostly talking about, right? Small to large businesses, home office applications. Fiber to the home. This is used to provide broadband services. And this is what I was saying earlier. A lot of homes that are being built now or retrofitted are being fitted for fiber to the home. For example, I have a gig of service. I have fiber to the home here. Long haul networks. So this is, fiber is the preferred way to carry data signals between countries. And typically it is going to go under the water, submarine cable networks. That is how this is how these countries are being connected so that we can communicate internationally. I've noticed the new iteration of the CCNA is asking a lot more questions about fiber and fiber optic. One of these questions is, what are the connector types on fiber? I do think it's important to look at these, understand them, be able to physically tell the difference. Here we've got a straight tip connector. I think an easy way to remember that is it's got this tip that sticks out, right? And in some ways it looks a little bit like a coaxial because of the way it's rounded. You push that in and twist it to lock it in. So a straight tip connector. An LC or a lucent connector, very, very common. Ask me in class, I can show you an example of some of these connectors. A subscriber connector, an SC. Now these are real little, okay? These are real little. And then finally, a duplex multi-mode LC connector, okay? So we've got the ST, the LC, there's actually the two LCs, and then an SC. ST, SC, LC, multi-mode LC. There's also different types of fiber patch cords. Okay, so we have the SC to SC patch cord. We have an LC to LC patch cord. Now this cable, we've got an ST with a termination of an LC. Also, here I have an ST to SC. A yellow jacket is for single mode, and the orange or aqua is for multi-mode. So multi-mode, single mode, multi-mode, single mode. Fiber is going to do a lot more for us in the terms of bandwidth as well as distance. So the bandwidth that can be supported by UTP cable is 10 megabits to 10 gigs, but we know that Really, it's not recommended for 10 gigs until you get up into like the 7, category 7. Fiber optic cabling, 10 megabits all the way up to 100 gigs, no restrictions. The distance, look, 1 to 100 meters, up to 100,000 meters. EMI, low EMI RFI, but it's still there. There's none when it comes to fiber optic. Electrical hazards, we could have some with UTP cable, Ethernet cable. There's no electrical hazards with fiber optic. Media and connector costs, super cheap for Ethernet and for copper. We're starting to get a little expensive when we're talking about fiber optic, especially because the tips have to be polished. It takes a skilled person to put the connectors on. It's just not as simple and easy. Installation, low skill level, high skill level. Safety precautions. Very low safety precautions are needed for Ethernet cable, copper cable, a little bit higher for glass, the fiber optic, because it is glass. Additionally, if you bend that glass too far, you can actually break the glass, and then those tiny little pieces can get into your skin, into your eye. Very difficult to take care of. Let's take another break. We have talked about Ethernet copper. We've talked about fiber optic light. Now we're going to be talking about the wireless media, microwave signals, radio frequency signals, right? Wireless signals. Properties of wireless. It carries electromagnetic signals representing binary digits, ones and zeros. It's using radio or microwave frequencies. This provides the greatest mobility. Wireless connection numbers continue to increase. We know that wireless is improving, but there are still some limitations. Just like the media that we talked about beforehand, each media has pros and cons. So one of the cons of the wireless is that its coverage area, right? The coverage area just isn't as expansive, and it can be impacted by physical characteristics. You know, have you ever been in a building where you just couldn't get a good signal on your cell phone? Maybe you were trying to use your laptop. That could be why, because there's a lot of physical impacts. Interference. Wireless is susceptible to interference and can be disrupted by lots of other common devices. Security. Wireless communication coverage requires no access to a physical strand of media. So again, that signal can be captured. There are software that allow you to look at that when the data that's being carried across the wireless. And also, it's a shared medium. Wireless LANs operate at half duplex, which we're going to be talking about. And that means that only one device at a time can send or receive. With Ethernet, we can send and receive at the same time. Fiber optic, we can send and receive at the same time, but not with wireless. The signal has to be sent and received before another one can be sent and received. The farther away a device is from the signal, the weaker that signal is. Now, that kind of happens with copper as well, right? With signal attenuation, we know that there's only so far that a copper cable can carry the data. Well, the same is true with wireless, but it's probably, even shorter. There are a lot of IEEE standards that it's very important that you learn. Same thing, you want to just kind of commit these to memory. They're going to come up all the time, whether you're dealing with a networking, if you end up working in the wireless field somewhere, telecommunications field, anything to deal with computers. Wireless standards are always going to be important for you to know and understand. So first of all, let's just know that the IEEE 802.11 is the standard that defines wireless, okay? Commonly called Wi-Fi. It uses something called CSMA, CA, and we're going to talk more about that too in future chapters. This stands for Carrier Sense Multiple Access Collision Detection or Avoidance. It is the way that the radio frequency can avoid a collision or detect whether there's going to be a collision. The variations of the Wi-Fi standard is 802.11a, B, 802.11g, 802.11n, 802.11ac, and 802.11ad. Recently, the wireless standards and the wireless world has changed this convention to be an easier numbering system. The problem is it hasn't been adopted throughout the world or throughout all of the standards organizations yet. So there hasn't been a real conversion over. What you might want to notice here is what determines whether it's an A, B, G, N, AC, or AD is the signals that it can carry and the speed, the bandwidth that it's capable of doing. Okay, the 802.11n is kind of the new preferred, and then the 802.11ad. So notice here, 802.11n, you can carry 600 megabits per second, and you can run on a 2.4 or a 5 gigahertz channel. Okay, 802.11ad, 7 gigs per second, and we can run on 2.4, 5, or 60. The common one now is 802.11n. Bluetooth, that has its own standard too. It's also a wireless technology. And Bluetooth is going to be IEEE 802.15. It will support speeds up to 3 megabits. Remember, Bluetooth has a very small distance, right? So you can use Bluetooth headsets, but you've got to have your homing device really close by. And then WiMAX. I think it's a good idea to also know the standard for WiMAX. 802.16, 802.16. It uses a point to multi-point topology to provide wireless broadband. So you might see WiMAX in a city that's rolling out WiMAX so that people can be in their city and connect up to their WiMAX spot. It's growing in popularity, and certainly a lot of different cities are offering it. When thinking about a wireless LAN, what are the two devices you need in order for your wireless LAN to connect and work? Is it A, a wireless control module, B, a wireless access point, C, a wireless NIC adapter, or D, a wireless access adapter? So one of these up here is pretty easy. And I would say that that's a wireless NIC adapter. Because earlier in this conversation, when we first started talking about layer 1, we were talking about NIC cards and that every device needs to have a physical component in order to connect to a network. The second one, or in this layout, the first one would be a wireless access point. Our device needs an access point. And the second was that NIC adapter. So there will be a NIC card in the access point as well as the wireless adapter. And then we need to connect those up so that a wireless device such as a laptop or a cell phone can connect to it. The wireless access point concentrates the wireless signals from users and connects, usually through a copper cable, right? We need that physical connection to the existing copper-based network infrastructure such as Ethernet. A wireless NIC adapter. This provides wireless communication capability to each network host. Here's an example of the wireless access point. Okay, that pretty much does it for the highlights and the overview of Module 4. I do want to cover some of the Module 6 highlights and things to pay attention to. Notice we skipped from 4 to 6. And the reason is because Module number 5 is about numbering systems. Boolean, binary, and hexadecimal. And we will be covering all of those things through supplemental videos that are required to watch. And we will be doing examples every day in class so that we can practice at getting better at binary conversions and decimal conversions. Because we are covering so much of Module 5 throughout the class, I will not be making a separate video for Module 5. Instead, we'll be covering that in class. These are the Module 6 highlights and preview. Module 6, 7, and 9 are all related. What I've listed on this guide here is just that. It is a guide. It is not comprehensive. Modules 6, 7, and 9 have a ton of information. A good way to study for 6, 7, and 9 and to get to know what they're about would be to watch my video or one of the other videos and then read the module to see where your understanding lines up. And then bring your questions to class. Modules 6, 7, and 9 are talking about layer 2, the data link layer. So we are moving from layer 1 to layer 2. The first highlight point here is, what is the purpose of the data link layer? What are the data link sublayers? Along with that, what is their purpose? What are the different topology types? What does contention-based access control methods mean? What is used by the multi-access networks? Is it collision avoidance? Is it collision detection? Remember, we did mention this term earlier in this review. The difference between full duplex and half duplex. What are the layer 2 standards? We know that we covered a couple of layer 1 standards, including Wi-Fi, the 802.11, A, D, N, GC, etc. We want to know what the layer 2 standards are, and that's 802.3 and 802.11. Okay. What is the format of an Ethernet frame? It is really important to understand the Ethernet frame and the format of the Ethernet frame. We'll touch on that in Module 6, and then we'll dig deeper into it in Module 7. What is a MAC address? Where do you find a MAC address? Why do we need a MAC address? Okay. Also, there are some outstanding videos and animations in the NetAcad module. I strongly recommend that you watch those and that you review them and read those modules. Since we're here, I'm going to go ahead and give you a Module 7 review as well. I want you to, again, just realize they are related. Module 6 and 7, they build right on each other. A highlight for Module 7 is, what is the format of an Ethernet frame? More about MAC addresses. We also start talking about the MAC address table. How is a MAC address table built? How is it related to a switch? What are the speeds of a switch? What are the different forwarding methods that a switch uses? We want to review the data link sublayers. We're going to talk more about encapsulation and de-encapsulation. What is the role of error detection in switching? We'll talk more about hexadecimal, which is what we cover in Module 5. How does a frame get processed? What is unicast, multicast, and broadcast? We first talked about unicast, multicast, and broadcast in Module 2. Well, we're going to dig a little bit deeper into that now and see what role they have in the communication methods of switching. What is auto MDIX? Now, auto MDIX relates back to cabling a little bit. Watch all of the videos. They'll really help you. Make sure you are also watching the required videos about binary to decimal, decimal to binary, network addressing, whatever those required videos are, because we're going to be doing stuff related to addressing every day of class. I think that's it. Have a great day, and thank you for watching.